Okay, so we're going to discuss today about segments formed by chords, secants, and tangents. Let us first clarify that in this particular figure, XZ is a secant segment of circle A. So XZ is a secant segment. However, XY is an external secant segment of circle A. So this is your external secant segment. So let us begin. A theorem states that if two chords intersect in a circle, then the product of the lengths of the segments on one chord is equal to the product of the lengths of the segments on the other chord. So how is this done? This is your example. This only means that 2 times 6 is equal to 3 times 4. That is 2 times 6 is equal to 3 times 4. And that is true because that's 12 equal to 12, and that is a check mark. So how about on this one? The same theorem applies. So two chords are intersecting in the interior of the circle, meaning to say this length times this length. So 2 times 9 is equal to 3 times 6, which is going to be true because that's 18 equals 18, and that's a check again. So in this particular example, we have this chord times this chord, so 8 times 2. Is that equal to 4 times 4? And the answer is yes, because that's 16 equals 16, and that's a check. Theorem number 2 states that if two secants are drawn to a circle from an exterior point, such as these drawings right here, the product of the lengths of one secant and its external secant segment is equal to the product of the lengths of the other secant and its external secant segment. So let's review our terminologies. This segment right here is your external secant segment. The whole thing is your secant segment. So according to the theorem, this segment right here times the whole segment, the whole secant segment, is equal to this external secant segment times the whole secant segment. So how is this going to happen is you're saying that 2 times 9. So I hope you know where I got the 9 from. I got the 9 from 2 plus 7 because it's the whole thing. So this external secant segment is the 2. The secant segment is the 9. That would be equal to this external secant segment, which is a 3, times the 6. Now why 6? Because it's the whole thing. 3 plus 3 is 6. Let's examine this. So this now is going to become 18 equals 18. So that's a check. Now let's go to example number 2. Again, let me remind you that these illustrations are not drawn to scale. Therefore, don't feel weird that this is a 1, that's a 3. Okay, so let's go back to our theorem. The external secant segment 3 times the secant segment, which is the whole thing, which I'm going to add 3 plus 1 will be 4. So 3 times 4 is going to be equal to the external secant segment times the whole thing, which is 6. Why 6? Because it's 2 plus 4. So 2 times 6 is a 12. And this is also a 12. So that's a check. Let's now go to example number 3. Example number 3 is a little bit different. We have an x. So let's go ahead and solve for x. According to the theorem, this is going to look like 3 times 8 is equal to 2 times the whole thing, which is x. So this is 24 equals 2x. Divide by 2, divide by 2. Your x is going to be 12. So the whole thing is going to be 12. Now, another question that may be asked here is, how about this chord right here? So from here to here, how much is it? So very good. The answer is 10. And the reason why you got a 10 is because if this is 2 and the whole thing is 12, you subtract 12 and 2, making this chord become 10. Okay, so our third and final theorem for this topic is if a tangent and a secant are drawn to a circle from an exterior point of the circle, the square of the length of the tangent segment is equal to the product of the lengths of the secant segment and its external secant segment. What this means is, if you have the tangent segment AB and you have the secant segment BD and the external secant segment BC, this is going to happen. That AB squared is equal to BC times BD. So what's that again is AB squared is equal to BC times BD. So let's have some examples here at the bottom. So let's do this. So this right here is going to look like 6 squared equals 4 times 9. So once again, I don't want you to be confused. Mrs. Santos, where did you get the 9 from? It's not there. Remember, it's the product of the external secant segment, which is 4, and the secant segment, which is the whole thing. This whole segment right here is a total of 9. Therefore, it is 36 equals 36, which is a check. Okay, now let us go ahead and do the example for our next illustration. Okay, let me just move this a little bit. Okay, so now, since this appears to be your tangent segment, that's the segment that you're going to square, equals, this is your external secant segment 2 times the secant segment is the whole thing, which will amount to 8, which is 16 equals 16 is a check. Okay, now, the next example is AB is 10, so let me put that there. BC is 4, so put the teeny tiny 4 there. And you're looking for DC. This is your unknown. Now, what I know is I can go ahead and make this become my unknown. So let's go ahead and do that as your, in fact, you know what? Let's make this into Rx. Let's not do this for X. Let's remove that as Rx. I want the whole thing to be X because that's easier. So let's go ahead and do that. So now your AB is 10 squared equals your external secant segment is 4. Your secant segment is X. This is going to be 100 equals 4x. Divide by 4, divide by 4. That is going to be x equals 25. Now we're not done because we're looking for DC. If the whole thing is 25, all I will have to do is 25 minus 4 will give me the DC. Therefore, DC is 25 minus 4, and DC is 21. So once again, just to avoid the confusion, please take that off, the x there. We're deciding that Rx is the whole thing, and that's DC 21, which is because of 25 minus 4.